Okay, so till now what we were doing? Do you all remember? Anyone? Previously, what did we do?
Sir, Boltzmann constant law. Distribution law.
Boltzmann distribution law. And apart from that, we were discussing what? Gibbs paradox. Do you all remember? Gibbs paradox. Do you know what are paradoxes?
No, sir.
I think we have done in the astro. Do you all remember paradox? If all the stars were equally light up, then how come the night sky is dark? Do you all remember?
Yes, sir.
Okay, usually paradoxes are, suppose, let's say, this is you, and you made some kind of, let's say, you made some kind of time machine. Clear? And this is you in future, and you went to your past. Using this time machine, what did you do? You went to past, and you killed yourself. Clear? And you killed yourself. Now this paradox. Why?
So then how did I went to future, sir, if I killed myself in past?
Okay, exactly. Yeah, that those things are called what? Paradoxes. Clear?
Yes, sir.
So what about the Gibbs paradox? In Gibbs paradox, what did we do? Suppose we have a box containing gases, which is separated by a what? Partition. Okay. Now suppose you have a box which is filled out of what? Gas. Let's do it in a new page. You have a box which is filled with what? Gases. Let's say this is compartment A and this is compartment B. Clear? And the volume over here is V1 and the number of particle over here is N1. The volume over here is V2. The number of particle over here is N2. Number of gas molecules, let's call it. And between them, you have a what? Partition. Is it clear till here? Everyone?
Yes, sir.
Now what do you do? Initially, as the particle are or the gas molecules are moving all over the places, what they will have its own entropy. Let's say the entropy over here is S1. The entropy over here is S2. Clear? Because they will have entropy because they are randomly arranged. So when you remove the partition, what will happen? The entropy will increase or decrease. Increase, decrease, or remain the same. What will happen? Just think of this as in a room, you have a huge number of people which are tightly packed and are sitting over here. Clear? And same thing goes for here. A huge number of particles which are or people are tightly sitting over here. And when you remove the compartment, what will happen? The system will be even more random or it will be less random.
More random, sir.
So that's why what will happen? The entropy will increase.
Yes, sir.
The entropy will increase. Finally, what? Because the particle will or the air molecule will start mixing with each other. Clear?
Yes, sir.
So that's why what will happen? The entropy will increase because that is very simple to see also. Because you have particle, let's say, which is sitting over here, and now you have started increasing. Now previously, let's say this was the arrangement. Now those two particles are what? Distinguishable. Clear? For a distinguishable particle. Let's say you have A, B, C, D particle over here. A, B, C, D. E, F, G, H is sitting over here. Now if you mix these two, then when this, let's say this state or this cell was taken up by A, this was taken up by B, C. Now even what? Your E, F, G, H, either of this can enter over here. Clear? So number of what? Your microstate will increase, which will in turn increase your what? Will increase your what? Is the number of combination will increase or not?
Entropy.
Is this point clear why the entropy will increase? First thing is why the number of microstates will increase. Is this point clear or not?
Sure, because the randomness increases, sir.
Yeah, okay. Basically, the randomness will increase because they are different particles and they are mixing with each other. Now, next thing what do we do is, let's consider both the particle to be what? Indistinguishable. What does indistinguishable means?
Not distinguishable.
We cannot distinguish. If its particle is A, everything is A. Clear? Those are is indistinguishable particle. Now, if you remove the partition for an indistinguishable particle, let's do it in this manner. Let's say this is red, and this one was blue. Let's say these are different distinguishable particle. Okay, they are of different colors. Let's say. Now, next we consider a indistinguishable particle. Same scenario, we have an indistinguishable particle, but indistinguishable particle will sitting over here, or the molecules are sitting over here. Now, if we remove the partition, what will happen? The entropy will increase or decrease or remain same. Okay, the entropy will increase. Okay, who is Ritika? Or is it Indira?
Yes,
Okay, Indira is telling that entropy will increase. What about Ruben and the remaining? Ruben, what will happen?
Sure, no idea, sir.
Okay, you have no idea. Any guesses, Ruben?
Sir, no, sir.
Okay, it will increase or decrease or it will remain the same.
Maybe remain the same, sir.
Okay, it will remain the same. Change in entropy is 0. Change in entropy is greater than 0. And what about Sanjeev and all? Okay, now let me ask you one more question. Okay, previously what was the case? The two particles were distinguishable. Previously we had only A and B. Now all of a sudden C and D came over here. When you mix these two up. Okay, this is for a distinguishable particle. Now this C can sit over here. This C can sit over here because they are what? Distinguishable. Now, if we consider all the particle to be same, let's consider this as AA. Now putting this over here is same as having this A over here. Clear?
Yes, sir.
So what will happen? The entropy will not change because the randomness will not change because it's a indistinguishable particle because they are same particle. Let's say we have a seating arrangement in our classroom. Okay, let's consider a seating arrangement. Initially, I kept Ruben over here and Sanjeev over here and Indira and Ritika over here. Clear? Now I can bring Ruben over here and keep him over here and so on and so forth because all of you are what? Distinguishable. Clear?
Yes.
Now let's consider a system. Now what will happen? The randomness will increase. If I increase the size or if I introduce or bring Abhishek over here. Let's consider a very simple system. Okay. You have two rows. Over here, Ruben was sitting and Sanjeev was sitting. And over this desk, what? Ritika and Indira was sitting. Clear? Is it clear? And what did you do? Next, we took all of you and and there is another classroom where the different people are sitting over here. Let's say this is a chemistry class. And sometimes you have a combined class. Clear? So during the combined class, what will happen? During this arrangement, what? Ruben can be set over here. He can be brought over here in this desk, and Ritika can be brought over here. So the number of combination could be what? Number of combination could be what? Ruben sitting over here, Sanjeev sitting over here. Let's consider him as A, B, and C, D, and this has say different states. Clear? And the type of combination could be what? 2 over here, 2 people over here. But this 2 also can be exchanged. Ruben can sit over here. He can also come over here. Now the number of microstate will be what? A, B, C, and D. And similarly, what? B, this C will come over here. And A and D. Is it okay? Are you being able to follow? Now the Ruben has went over here. Now finally what we can have? We can bring both the people in front. And finally what we can have? CD and AB kind of thing over here. Clear? Now if all of them are, instead of being different people, if all of them are just Ruben, now, and if you add and bring this, now the desks are 4 and the number of people are also more. Now definitely the number of microstate will definitely increase. Why it will increase? Because these are different distinguishable particle. Clear? Now I can take Ruben to either to this, this, or this. So the number of combination will increase. Now, if this were exactly identical, then now the number of combinations are not possible. Because why? Because if it's 2, 2, then it will be A, and A, and A. Clear? And even if I mix and bring another student, even though we will get what? AA. There is no more combination, whatever we were having previously, possible to have more combination. So in short, because all of the particles are identical, so it does not know because how it has been set up. So that's why the entropy will not increase. Is this point clear or not? I think it's not clear. Basically, the particle are what? Indistinguishable, so the randomness will not increase. Because when it's C next to it, it seems like even if this molecule comes over here, it will feel like the same molecule which is sitting over here is sitting over here. Because they are what? Indistinguishable. Because they cannot distinguish between different states. Clear?
Yes, sir.
Let's consider this very simplest system. You have a cell 1 where you have a single particle A, and you have another system where it's a single particle B. Is it clear till here? This is the simplest system possible. Over here, on one system you have A, on the other system you have B. Clear? Initially it will have how many combinations is possible? Only one. How many combinations are possible? 1, because there is only a single system and only a single particle. So the only possibility of is just keeping it over there. So the number of combination, number of microstates over here is what? Again 1. Now if you combine these two systems, then what you will get? A and B. Clear? Is it clear? Now the number of combination will be what? Either A and B, or B and A is also possible. Now can you see the number of microstate has increased to 2, or basically means the randomness has increased, because the entropy is proportional to what? The number of microstate. K ln of omega, log of omega, or ln of omega. Do you all know this? Because the entropy is proportional to the number of microstate. Now the microstate has increased. So that's why your entropy will increase. So next, consider this system where you have only A and A. Now, even if you combine this, so what is the total number of microstate over here? Only combination is only A and A. So that's why the entropy will not increase. Now, is it clear? Ruben? Ruben? Indira? Is it
Yes,
clear
sir.
now?
Yes, sir.
Yes, sir.
Okay. Then finally, what we move to? So if the particles are what? Indistinguishable, then the change in entropy is zero. Change in entropy is zero. So, and there was a numerical expression which was given that the entropy should be given by what? Entropy is given by S is equals to pi by 2 n plus alpha n plus log of n factorial. This is what you will end up when you consider where alpha is a function of L. Let's say this is here. Theoretically, the entropy of a system was given by this. Initially, let's consider both the system individually. Clear? Let's consider this as system A and system B. Number of particles was N1 and volume was V1. And this was N2, V2. Clear? So let's consider for system A. Entropy for system A is how much? Pi by 2 N1 plus alpha N1 plus log of N1 factorial. Similarly, the entropy for SB is how much? How much? Alpha is a function. Let's put it as alpha 1 and alpha 2. And log of N2 factorial. Clear? Now when the now the total entropy is how much? SA by SB. Let's add this two. And let's consider number of particle and the volume to be same. So that's why what will happen is let N1 equal to N2 and volume V1 equal to V2. When V1 equal to V2 and N1 equal to N2, your alpha N1 will be equal to alpha 2. Clear? For a time, just consider this as a function. So SA will be how much? 5 by 2 N1 plus N2 S total entropy SA plus SB. Initially, okay, this is initially what was the entropy? Will be how much? And the particles are identical, okay? These particles are identical. 5 by 2 N1 plus N2 plus twice of alpha. Let's put this as, okay, alpha 1 N. Let's put this as N, this as V, and this is as alpha. This becomes twice of alpha log of then basically N1 plus N2. So finally you'll end up with what? 5 by 2 twice N plus 2 alpha N plus log of 2N factorial. Clear? Is it clear? 5N plus 2 alpha N plus log of 2N factorial. This is here entropy before. Now after mixing, what will happen? After mixing, what will happen? Oh no. Is it clear till here? I'm asking to everyone. Ruben,
Yes, sir.
you have a two box, both the sizes were same. It was V and number of particles was N, this was V and number of particles was. For timing, you just take this formula as granted, okay? Later we'll derive it, don't worry. S is equals to 5 by 2 Nk minus N alpha plus log of N factorial. Let's do it tron by tron. For let's consider this as system A and this is system B. For system A, we have what? 5 by 2 Nk minus N alpha plus log of N factorial. For SB, how much we'll get? Exactly identical. Sorry, this is positive. Plus log of N factorial. Both are indistinguishable. Clear? Indistinguishable. So that's why you have a distribution or the entropy of this form. Now, initially, before the partition was opened, the total entropy is how much? We can just add this two up. SA plus SB will be how much? This two will add up to give you what? 10 by 2 Nk. Sorry. 5 Nk. This two will add up to give you. This will give you 2 N alpha. And how much this will give you? 2 log of N factorial. This is here initially. This was your entropy initially. Now next is you open this. You take out the partition between these two system. Then what will happen? The volume will increase from what? V1 plus V2 and number of particle will be N plus N. So it will be 2V and 2N. Is this point clear? So the final entropy will be how much when the partition basement opened is exactly we will use the formula over here 5 by 2 N will be how much? 2N K plus 2N alpha plus log of 2N factorial. This 2 will cancel out. So final will be how much? 5Nk plus 2N alpha plus log of 2N factorial. Now, if you want to check the change in entropy, then what do? This is after and this is before. You just subtract this 2. This is Si, let's write this initial. SF minus S initial will be how much? This 2 will cancel off. If you can directly see from here, 5Nk minus 5Nk. This 2 will cancel out. If you subtract this 2, what will happen? This 2 will cancel out. Only the term that will be remaining is what? 2 log of N factorial minus log of 2N factorial. Is this point clear? There you go, sorry. Initial, no final, no. First one is, so it will be log 2N factorial minus 2 log of N factorial. Indira, is this point clear? Indira?
Yes, sir.
Okay. Now is this 2 term 0? But actually what we wanted our entropy to be 0. But actually we are from seeing here this term, 2 terms are not 0. Because you can directly verify this. Because if you use the Stalling approximation, what you will get? 2 ln of 2n minus 2n minus how much over here? 2n log of n minus n log of n minus what? N twice of n. 2n log of 2n minus, because this 2 will cancel out. and we'll get out what? This. You can take out 2n common. So basically it will be log of 2n minus log of n. Clear? Now this is just from seeing from over here also one can see this is not 0. And actually what do we want? The change in entropy to be what? Change in entropy, how much do we want? Ruben, change in entropy, how much do we want?
0, sir.
We want change in entropy to be 0. Why are we getting 2n over here? Because it's 2n. Because log of n factorial is n log of n. Yeah, clear. So this actually what you can do is this thing. What you can do, 2n, you can take it out. This you can put 2 product of this 2 log 2 plus log of n. One can always write this. This 2 will cancel out and it will be 2n log of 2. Now change in entropy is not 0. It's saying that the final entropy is more. The entropy increases, but the particles are identical, so there shouldn't be any entropy. The change in entropy should be 0 because they are identical, so there shouldn't be any more randomness. So main problem starts from where? From this term. If you want to see, because this term, 2 term exactly cancels out. Can you see? So for this formula to be consistent, what we can write? The entropy can be written as what? S can be written as 5 by 2 nk minus plus of alpha n. Is it clear? If we remove that additional term, then what? The change in entropy will be exactly what? 0. So this is how you remove the paradox. The paradox. So actually the paradox was what? If we have a system which has what? Molecules which are sitting over on 2 different systems and there is a partition in between. Now initially there will be certain entropy between these 2 systems, and if they are identical and if I open this partition, then what will happen? The change in entropy will be 0 because they are identical. Now according to the formula, then what do we get? The change in entropy to be positive. The final entropy is more as compared to previous entropy. So there is a paradox. Clear? Intuitively, we think that the entropy should be 0, but according to the formula, what do we get? We get the entropy to be, change in entropy to be positive. Clear? So the paradox has been removed by doing what? By considering or removing the additional term in a formula, which is log of n factorial. Clear? Is it clear? Do you have any questions? Any questions? Okay, good. So I'm going to stop this